Here we go.
Okay.
Right. Thank you, everybody, for coming. My name is Dean Lee, and I'm a professor of physics at the Facility for Rare Isotope Beams. And this public talk is part of an initiative at the Facility for Rare Isotope Beams called the Advanced Studies Gateway. The goal of the Advanced Studies Gateway is to, simply put, inspire people. We bring together researchers, innovators, creative thinkers, artists, and performers from all fields and strengthen ties between Michigan State University and the community. Today, we have the pleasure of presenting a public lecture by Professor Stephen Simon on knots, world lines, and quantum computation. Stephen Simon has been a theoretical physics professor at Oxford University since 2009. He received his PhD in physics from Harvard University in 1995. He was then a postdoctoral researcher at MIT and a staff member at Bell Labs. From 2000 to 2008, he was the director of theoretical physics research at Bell Labs, and he is known for his work on topological phases of matter, topological quantum computing, and the fractional quantum Hall effect. He is also the author of a popular introductory book on solid-state physics that is, quote, guaranteed to be the funniest book on solid-state physics you will ever read, unquote. If you have any questions during this talk, please type them into the chat. And at this time, it is my great pleasure to introduce Stephen Simon.
Thank you. It's really a pleasure to be giving this talk. So I've subtitled my talk here, Topological Quantum, which is another way to say what I'm about to speak about. This subject, topological quantum, sits at the nexus, sort of an intersection of several fields of modern science. I'm a condensed matter physicist. That means I study stuff, matter, often matter where types of materials where quantum mechanics are extremely important. And within condensed matter physics, the ideas of topological quantum are extremely prevalent in modern research. But the same ideas are actually very prevalent in the fields of quantum computation and quantum information sciences. People doing computer science and in the quantum domain are very interested in these ideas as well. And they give us, as I'll explain as we go along, some of these ideas give us a way to potentially do computations that are otherwise essentially impossible. And many of the ideas I'll talk about actually grew out of the mathematics community and the string theory community, particularly people thinking about quantum gravity, starting back in around the 1980s, people who developed what we call topological quantum field theories. But the real origins of this field go back much further, really into the 1800s, and that's where I'm going to start this story, and we'll go from there. So I'll start by taking a long detour into well, history and mathematics, and eventually I'll come back to physics and knots, world lines, and kind of quantum computation. So our story starts up in Scotland in 1867, where there are two very well-known physicists. The first one, William Thompson, that name may not be familiar, but he's better known by his name, Lord Kelvin. Probably many of you know some of the things that Lord Kelvin did, besides getting the scale of temperature named after him. Very important physicist for many reasons. The other physicist who was working with him was a guy by the name of Peter Tate. Now, that name is probably a lot less familiar to most people, but he was a very good scientist as well, a very close friend of Lord Kelvin's. They worked together throughout their lives. And in 1867, they were interested in a phenomenon, actually, of fluid flow. So the phenomenon is known as a vortex ring, and it was familiar to everyone, really everyone everyone in the world back then. And let me remind you what a vortex ring is. Let's imagine you have a invisible loop hanging in the air there, and imagine that you have fluid flowing around this loop in this way, around this way and around this way and around this way, and the fluid flows around that invisible loop, circulates in this way, and that entire object moves forward out of the plane of the board at you. Now, back in the 1800s in Scotland, they used to do this very strange thing called smoking tobacco, and they don't do that anymore because we know it's bad for you, but I'm told it's a little bit like vaping. And you know, a talented smoker, one of the great things about giving a talk over Zoom is you have no idea if anyone's laughing at your jokes. So I'm just going to assume everyone finds them funny. I'll keep telling them. So you know, but people were familiar with the idea of a smoke ring, because you can produce one of these with your mouth if you're a talented smoker. And they wanted to study this. And what Peter Tate did is he actually built a machine to produce smoke rings. And they're actually quite easy to make. If you take a tube like a garbage can, you fill it with smoke, and you slap the back of the garbage can, a smoke ring will come out the front. And he showed this to his friend Lord Kelvin, and Lord Kelvin was amazed. He said, "Wow." He had a number of simultaneous epiphanies seeing this this demonstration. Now, the first epiphany is something we still teach in our undergraduate fluid dynamics courses. It sometimes goes by the name of Kelvin's circulation theorem. Maybe I'll write that down, circulation theorem. And the content of Kelvin's circulation theorem is basically that if it weren't for the friction in the air, dissipation, viscosity, the fact that air is not a perfect fluid, if it weren't for those facts, then this fluid flow configuration, this smoke ring, it would just keep circulating forever and ever and ever. And the fluid would keep floating, going around and around and around and around. It would just never stop. Now, such fluids which are perfect without any dissipation, without any friction, do exist, but Kelvin didn't know about any of them. And he started thinking to himself, well, where might I find a fluid which doesn't have any dissipation? Now, one example of such a fluid without any dissipation, without any friction, is superfluid helium. Now, if you just take regular helium, the element helium, and you cool it down to 1 or 2 degrees Kelvin above absolute zero, and it becomes superfluid. And if you start the fluid flowing in this way, sort of like a smoke ring, you blow a smoke ring in the superfluid helium, that smoke ring will keep circulating around and around and around. It will actually never stop. Now, Kelvin unfortunately didn't know about superfluid helium. In fact, in 1867, helium as an element hadn't even been discovered. And also, he didn't have any way to cool things down to 1 degree Kelvin above absolute zero, although he knew there was such a thing as absolute zero. He didn't know how to get there. So he didn't know about that. But he did think that he knew about a perfect fluid. And it's actually a famous mistake in the scientific literature. And this famous mistake is known as ether. Now, what is ether? Ether is supposedly a perfect dissipationless, frictionless, perfect fluid that fills up all of space. And the scientific community believed in ether in the 1800s for very good reason. And the reason they believed in this is they could, they understood a lot about waves. They understood that when they saw a wave on water, what they were actually seeing was water sloshing back and forth. So here's a wave on water, and what they realized it was water moving back and forth. And they understood that when they heard a wave of sound in the air, what they were actually hearing was air moving back and forth. And that was what makes sound. And they understood that light is a wave, or it had wave-like properties, and so they figured something had to be moving back and forth to carry this wave, and they called such a thing ether. And the idea of ether actually goes back several hundred years before Kelvin. It goes back to the French philosopher René Descartes, actually, who thought this up. He just said, I think, therefore it is, and he created ether. That was another joke in case you missed it. But it really was due to Descartes, the invention of ether. And the entire scientific community, everyone believed in ether in the 1800s. And they knew that this ether stuff had to be extremely dissipationless and free of friction, because you can see stars extremely far away. And if there was any friction in this ether fluid, the light wouldn't make it from the star to us to see. So on the one hand, Kelvin had his circulation theorem, which tells him that if it weren't for the friction, in the fluid, this fluid would keep flowing around and around forever. And on the other hand, he believed in ether as being a perfect dissipationless fluid that fills up the entire universe. And so that got him thinking, what then is a vortex ring? What is one of these smoke rings in this ether? And he came to a rather remarkable conclusion. He said, oh, well, this smoke ring in ether is probably an atom, like maybe helium, hydrogen, for example, the simplest configuration of fluid flow. We'll call it hydrogen. And then maybe you could have something like this, where you have two rings which are linked to each other like that, and the fluid flows around this one this way, and the fluid flows around this one this way. And because of the circulation theorem, this fluid flow configuration should last forever. It should never stop. And maybe this is a hydrogen molecule, H2. And then maybe you could have something more complicated, something like this, where, let me see if I can draw this properly. Okay. And then it goes like this. So you have sort of a knot, and then the fluid flows around this way, and around this way, and around this way, and so forth and so on. And this fluid flow configuration should also be stable forever. It should last forever. And maybe this is a more complicated atom, like maybe lithium. Now this what became known as Kelvin's vortex theory of the atom sounds completely bonkers to us now, because we know that atoms have nothing to do with vortex rings in the ether. In fact, we know there's no such thing as ether. That Einstein proved that in the early 1900s. And we know about, protons and neutrons and electrons and other things that make up atoms. It has nothing, this is not what makes up an atom. We all know that. But it actually sounded like a really good idea in the 1800s. And a lot of very serious scientists, people like Maxwell, Kirchhoff, Helmholtz, besides Kelvin himself, and took this theory extremely seriously. And they spent quite a while thinking about it. Now, some people criticized the theory, and one of the people who criticized this theory right away was his friend Peter Tate. And Peter Tate said right off the bat, he said, well, it's a beautiful theory, but it doesn't predict anything. It doesn't predict the masses of the atoms. It doesn't predict the electrical properties, their optical properties, or chemical properties. It doesn't predict anything that you would want the theory to predict. So, it's a nice picture, but it's probably wrong. Nonetheless, the scientific community took it extremely seriously for about 10 years or so before everyone more or less gave up on this theory, because of exactly the reasons that Tate had said, that it didn't predict anything. It wasn't very useful. But at the end of those 10 years, Peter Tate came back from his little vacation golfing. He was actually a fabulous golfer. He's a fabulous rugby player too, a great athlete, as well as a great scientist. And so he spent those 10 years while everyone else was thinking about the vortex theory of the atom. He was off golfing, and he came back from golfing at the end of 10 years, and he said, well, maybe even though this theory doesn't predict anything that you would want it to predict, maybe it is still a good theory. And what we really need to do is we need to understand this theory better in order to understand how it tells us something about the periodic table of the elements. So he set himself a little task, which was to build a periodic table of all the possible knots. This is the simplest knot. This is the next most simple knot. This is the next most simple knot, and so forth and so on. And he studied knots in great depth. He became what we view now as the father of the mathematical subfield of topology, known as knot theory, the study of knots and knotting, which is an extremely important, extremely rich subfield of mathematics, and it's very important for physics, as we'll see. Now, I will explain to you in a few moments what it was that Peter Tate understood that was so important. But before leaving this historical story, I should tell you the end of the story. So, along about the 1900s, Peter Tate started getting really depressed. He discovered an enormous amount about the mathematics of knots. In fact, some of his theorems and some of his conjectures about properties of knots were not proven until after the year 2000. So he's way, way, way ahead of his time. he discovered an enormous amount of mathematics, but of course he was no closer to understanding anything about atoms or the periodic table of the elements. And around 1900, he writes some letters to his friend Lord Kelvin saying that he's rather depressed about the situation, that he's wasted so much of his time working on studying knots, and in fact, this isn't really going anywhere. It's really just been a waste of his time. The next year, he had a son, Freddie Tate, and if you're a huge golf fan, you'll know the name Freddie Tate. He was a champion of the British Open, and his son Freddie was killed in the Boer Wars in South Africa the next year, and that put Peter Tate into a terrible depression, and he died just a few months later, extremely sad, obviously at the loss of his son, but also having felt that he wasted so much of his productive scientific life on this theory that just wasn't going anywhere. And what Peter Tate didn't realize is that his work on the theory of knots was going to be extremely important for physics, not of course for building the periodic table of the elements, but for doing other things much later on. But he didn't live to see that. Okay, so what was it that Peter Tate put his finger on that's so important? Well, the fundamental question in the mathematics of knots is whether two knots can be deformed into each other without scissors or they can't. So let me draw two pictures of knots. So here's a simple knot. We saw that before. We called it hydrogen. And then let me draw another knot here. Very, very simple knot. This sort of looks like a more complicated figure 8. And the question is, are these two things really the same or are they different? In other words, could you take this knot over here and deform it without using scissors, without cutting, just stretch it and pull it until it looks like this? If you can, we say that those two are topologically equivalent. In other words, it's only just one entry on Peter Tate's periodic table of the knots. It's not two different entries on Peter Tate's periodic table of the knots. If you can't deform this into this, then there are two different entries on the periodic table of knots. Now this, we're all pretty smart, and we can see that really all you have to do is if you pull this string underneath here and this string over here, then it just opens up into a simple circle like this. And these two pictures are obviously topologically equivalent to each other. They can be deformed into each other without cutting. But actually it becomes rapidly extremely difficult to tell when two things are the same and when they're different when you have more complicated knots. For example, this knot is different from its mirror image. And that was not proved until the 1920s, a little bit more complicated to do. So, when you have a really complicated knot, it's very hard to tell if it's the same or different from another knot. So what you need is a tool, a mathematical tool. And what we call these mathematical tools in modern era is a knot invariant. And a knot invariant is a mapping from a knot or a picture of a knot that you draw on paper to some output. And the output can be a number or a polynomial or a symbol of some sort. It's not so important what the output is. What's important is the set of rules that takes you from the input to the output. So you cook up your set of rules in such a way that two equivalent knots, two knots that can be deformed into each other without cutting, always give you the same output. Okay, so the idea is you have two really complicated knots, and you don't know if they're really the same knot or if they're different, if they can be deformed into each other. You put them into your set of rules, you turn the crank. If you get two different outputs, then you know immediately these two knots are fundamentally different. They can't be deformed into each other without scissors. And so this is an extremely useful thing to have if you're building a periodic table of the knots. So to show you how this works, I'm going to define a particular knot invariant, which is not only a particularly easy one to define, it's also a very useful one for physics. It's sometimes known as the Kaufman invariant or Kaufman bracket, and it is named after its inventor. Its inventor is Vaughan Jones. Okay, that was a joke. Also, it's not named after the inventor was Vaughan Jones, but it's named after Louis Kaufman. So Vaughan Jones is a very famous mathematician who just passed away earlier this year. He won the Fields Medal. That's the It's like the Nobel Prize of mathematics for his work on knot theory. Louis Kaufmann is still alive. He's a very good mathematician. I believe he's still in Chicago. And what he did, which is probably at least as important as what von Jones did, is he managed to take what von Jones was doing, which was fairly complicated, and he simplified it so much that I can explain it to you in about 2 minutes, which is what I'm going to do. Okay, so in order to define this Kaufmann bracket invariant, this knot invariant, we need a couple things. The first thing is we need to choose a number. We'll call it A. A stands for a number. That's why we call it A. And for now, we're just going to leave it a variable, but we might give it a value in a little while. That's easy. So, okay, you pick a number, whatever number you like for now. And then the first rule is really simple. If you ever have a loop of string like this in your picture, you can replace that loop of string in your picture with the following combination: minus a squared minus a to the minus 2 power. And that combination of variables occurs so often, we give it its own symbol. We call it D. So it's a really simple rule. A loop of string, as long as there's nothing going through the loop of string, is worth D. Okay, that's the first rule. Really simple rule. The second rule is a more complicated rule, and I'll try to explain it as simply as I can. If you have in your picture two strings that cross over each other like this, you replace them. You place that picture with two pictures. In the first picture, the two strings go vertical like this. And in the second picture, the two strings go horizontal like this. And then we put prefactors out in front of the pictures, A and A inverse. So what am I doing here? I'm doing some sort of algebra with pictures, and I'm replacing one picture with the sum of two pictures with prefactors out front, okay? This may seem complicated, but I'm going to do an example of it to try to simplify it, okay? All right, these are the only two rules you need. But I'm going to draw a third rule. I'm going to cheat a little bit, draw the third rule. A third rule is going to look exactly like the second rule, except all the pictures are rotated by 90 degrees, okay? And the reason I'm doing that is because it's a lot easier to draw the picture twice than it is to ask you to rotate your head in a few minutes. So, okay, so it's really just two rules, but I've drawn three. Okay, so now let's try to evaluate before your very eyes. I'm going to try to evaluate the Kaufmann invariant of this knot here. So let's copy this and bring it down here. Before your very eyes, let us try to evaluate the Kaufmann invariant of this knot. Okay, so what do? We look at this picture and we see that there is a crossing of two strings here. And that crossing there looks exactly like this crossing here. So I can replace that crossing with, oops, I want to make it black still. It's A times vertical plus A inverse times horizontal. And so that's just filling in this where I had this, okay? And then everything else in this picture stays unchanged. Above, it gets connected up like this, and below, it gets connected up like this. Okay, so nothing else in the pictures have changed. Okay, so that is everything you need to understand the rest of this talk. This is the most important moment of your day, maybe of your week. Okay, it may not be the most important moment of your week, but if you understand this, you'll understand the rest. So, okay, so what do we do now? If we look at these two pictures, in these two pictures, there is another crossing here. And this crossing looks like this. So we should use this rule, this lower rule, to remove this crossing as well. So let me do that fairly quickly. So first I'll bring down this A, and then that's this A here. I just moved that down. I opened up a bracket, and then I'm gonna plug in this rule again. This is actually the lower rule here I'm gonna use, and I will get A times horizontal plus A inverse times vertical. And then I fill in the rest of this knot exactly as it is in this picture here. So this kind of looks like this, and this kind of looks like this, and this kind of looks like this, and this kind of looks like this. Okay, and then I do the same thing here. I bring down the A inverse here. So then I have A inverse, oops, A inverse, open up the bracket, and then I have A times horizontal plus A inverse times vertical. And then everything has to look exactly the same as it is above. Like this, like this. Okay, good. So now, okay, it was just a little bit of maneuvering there. But in the last step, I now use this rule that each circle there gets the value d. Okay, so each time I have a loop, nothing crossing and nothing, there's no crossings left in any of these pictures. So each loop gets replaced by a factor of d. So let's just do that. So now I get a squared. There's two loops here. So I brought these two a's together to get a squared. So I get a squared times d squared. Then this a cancels this a. There's one loop here. So that gives me d. Oops, d. This a cancels this a inverse. And I have three loops. So that's d cubed. And then these two a inverses come together to give me a to the minus 2 plus a to the minus 2, 2 d's, d squared. Two loops gives me 2 d squared there. Okay. Then let me just group some terms together. So this is, I can just group these terms together. The first term and the last term, I'll bring them together. So I'll have a squared plus a to the minus 2 times d squared plus d cubed. And then you'll remember from up here that d is minus a squared minus a to the minus d, or other words, a squared plus a to the minus 2 is minus d. So we can replace this combination here with a minus d. So that means this whole term here is minus d cubed. This minus d cubed cancels this d cubed. And at the end of the day, all I get is d. The end. Yay. Yay, that's the end of the calculation. Okay, that's all the math I'm going to do. If you followed that, you're in good shape. That's it. So why is this so exciting? Why does this get a big yay at the end here? Well, way up at the beginning of the calculation, way up here, I had this funny looking knot. Secretly, I know that this knot was just a loop. Nothing more than a loop. I made it look a little complicated because I twisted it up a little bit, but it's just a loop. And the value of a loop is d. I made the knot look more complicated, but at the end of the day, when I calculate this Kaufman bracket invariant, I still get d at the end. And that's how knot invariants work. I could have folded this thing over 100 times and made it look incredibly complicated, and still I would have gotten d out at the end of the day. And that's how these knot invariants work. And so you can imagine how this could be extremely useful for building a periodic table of knots. Now, if you're extremely clever and you're thinking very hard, you will realize that I've actually lied to you a little bit. And actually, I've lied to you in several ways, but I've lied the way I'm going to explain to you why I lied to you is maybe the most crucial one. That it's not actually as useful as it looks. And the reason it's not as useful as it looks is because it turns out to be very hard to calculate Kaufman invariants of more complicated knots. Why is that? Well, this knot over here has two crossings, this one and this one, and I ended up with 4 diagrams. If I had had 3 crossings, I would have gotten 8 diagrams. If I had 4 crossings, I would have had 16 diagrams. If I have a knot diagram with n crossings, I would get 2 to the n diagrams. Now, the problem is it's really easy to draw a picture of a knot with 100 crossings. And the number 2 to the 100th power is so enormous that even the world's biggest computer working for 1,000 years would never be able to come up with an answer. See, this is the problem with exponentials. Exponentials always end in great sadness and misery. And that's exactly what's happening here. For a complicated enough knot, you have sadness and misery that you just can't calculate. Okay, so we'll come back to that issue in a little bit. But what I'm going to do now is I'm going to try to relate all of this to a bit of physics. So We're going to turn the page on leave knots behind for a moment, and I'm going to introduce a few concepts from physics. The first concept is the idea of a world line. Now, a world line is really nothing more than a bookkeeping technique, and you've probably even seen it before in high school math or something. And let me give an example of this. Let me draw two axes, a little graph here. The horizontal axis is going to be your location, and maybe I'll start here. My location is home. My location is work. I don't know. Maybe there's another location out here, a pub out here, it's close to work. And then the vertical axis is time. So here I'll have 8 a.m., maybe 9 a.m., maybe 5 p.m., maybe 6 p.m. And I can draw my my location throughout the day on this graph. So at 8 a.m. I start out at home, and then I go to work. I walk to work. It takes me about an hour to get to work. And at 9 o'clock, I'm at work. I stay at work until 5 p.m. And then maybe I go to the pub. And then at 6 o'clock, I decide to come all the way home. Okay, I get home by 7. Okay, and now this line here is known as my world line because it tells you where in the world I am at any point in time. All I have to do if I want to know where I am at 3 p.m., I just cut this line at 3 p.m. and I say, oh, I'm at work at 3 p.m. Okay, it's really just a bookkeeping trick. It's very convenient if you're thinking about both space, location, and time at the same time. Okay, so here's a fact, an interesting fact, that we can do experiments. We can do experiments on two-dimensional systems. In other words, on things that live in flatland, on the surface of a substance, on a single atom thick layer of graphene, for example, a single atom thick layer of carbon, for example. Things move in strictly in 2 dimensions. So if we're doing things in strictly 2 dimensions, we can do the same bookkeeping trick as we just did a moment ago, and it's going to look a little bit different, a little bit more complicated. So here's time again, and then we have, I'm going to draw my 2-dimensional plane here. Here's my 2-dimensional plane, and that's my location in my 2-dimensional plane is drawn down there. And then we can imagine taking objects on my 2-dimensional plane. Maybe my object in my 2-dimensional plane starts at this position here, and then as time moves on, it moves to some other position here, and then moves back to this position here. So this particle, whatever this particle was, it started at this position, it went to work, and then it came back home, okay, after some time. Now I can do that with another particle at the same time. Here's another particle. It starts over here, and here it went behind that one, but then it might go in front of this one like that. Now you might see where I'm going with this, because you will notice the world lines of these particles have now formed some sort of knot, world lines or braid, that one knot went behind the other, one particle went behind the other, and then later it went in front of the other, okay? And if you look at that diagram, you will see that there is a knot in that diagram, okay? So this is the first thing we're going to have. We're going to have knotted world lines. Now there's one more thing we need, which is basically, Einstein's famous equation, E equals mc squared. Now, if you've never seen that before, obviously it's a very beautiful equation. Einstein got famous for it. You've probably seen it written in lots of places before. I'm not going to explain it to you in detail, but basically what it means for us is that you can trade energy for mass. One way to do that, for example, is you can put in energy in the form of photons, very high energy photons, and those photons go in to a system, and out comes a particle of matter, and its opposing particle of antimatter. you pair create matter and antimatter out of the vacuum by putting energy in the form of photons. Okay, this is basically what Einstein's E equals mc squared means. The energy and mass can be traded for each other. Now you can try to do the same experiment in reverse. Let's try to do the same thing in reverse. We'll put in, actually, let me get a new page here. We'll start with our matter and antimatter. Here's our matter and here's our antimatter. We'll bring them together. And what we discover is actually kind of interesting as a result of quantum mechanics, that more than one thing can happen. One thing that can happen is the photons come out, releasing the energy. Photons come out. So the matter and the antimatter can annihilate and produce the photons. On the other hand, another thing that can happen is that they can form a bound state like this that refuses to annihilate. It's forming like an atom that they stick together, but they do not go back to the vacuum. They do not release photons. And there's some probability of each of these two things happening. So it's probabilistic result. And this is something probabilistic. This is something that drove Einstein crazy. He said God does not play dice, but actually it turns out that God does play dice, and it's okay in quantum mechanics that you have more than one possible outcome of an experiment, and they happen probabilistically. So we have to get used to that idea as something that can happen in the outcome of our experiment. Okay, so let's now try to do an experiment. Here again, we're going to have time going vertically. We always know time is always going to go upwards here. Time is up. Time is up because time is money, and money always goes up, or something like that. Okay. Yeah, if people don't laugh at that, it's totally okay. All right. So here's my experiment again. So what I'm going to do in this experiment is I'm going to we start with nothing. We start with just a vacuum state. So we can think of this as just being, you know, my sheet of graphene, you know, with just everyone sitting in the ground state, unique ground state, nothing exciting happening, everyone just sort of sitting still, zero temperature state of the system, a two-dimensional system at my initial time. But then after some amount of time, I'm going to put in some energy, maybe in the form of photons here. And what will happen is I will create a particle and its antiparticle. Okay. And then maybe I'll put in some energy over here, maybe as a photon, and I'll get out a particle and its antiparticle, particle and its antiparticle. And then these particles, they can move around in the plane. And, you know, at some time, this one maybe goes around the other, and they come back together like this. And we try to bring them back together at some later time here. Now, when we bring these guys back together, there is an outcome, which is one of two possible things. Either these particles reannihilate, releasing the photons back from where they came, or they form bound states that do not, that refuse to annihilate. Now, here's the interesting fact, that particles in two dimensions exist such that when you do this experiment, the probability of all the particles annihilating, is equal to up to a normalization constant, which I won't mention, is the Kaufman invariant of the knot squared. Absolute value of the Kaufman invariant of the knot squared. Okay. Now, that result should be a little bit surprising to you. Well, okay, it should be surprising to everyone. So let me explain to you why it might be surprising to you. We're used to the idea in physics that when we do an experiment, a lot of the details of the experiment matter. So it matters, for example, exactly the path that these particles take. It matters, you know, how long these particles lived before you bring them back together. It matters how close they got to each other when they got close to each other. It mattered how fast they were moving when they went around each other. And what I've just told you here is that it really doesn't, none of those things matter, that I can deform this knot and to make it look a little different, make it look like this. This would still have the same Kaufman invariant as the knot I had there a moment ago, and therefore it should give the same output. Therefore, the probability of annihilation should be exactly the same. What I'm telling you is the only thing that matters is the topology of the knot, nothing else. Only the topology of this knot matters, and that's surprising. The fact that such particles exist is something that should be surprising. Now, this a rather interesting connection between the theory of knots and physics or quantum physics was made rather famously by Ed Witten. Okay, I'll put his name in blue there. Back in 1989, in some work that won him the Fields Medal for his work on knot theory. Ed Witten, if you don't know that name, he is probably the world's most famous string theorist, one of the inventors of the ideas of string theory, which is an attempt to unify quantum mechanics and gravity, one of the great outstanding puzzles of modern physics. And Witten is one of the leaders of that field, but what he won his Fields Medal for was actually for knot theory. Now, there is something that I haven't told you yet, and that is when we define the Kaufman invariant, you recall that the first step way back up here was that you have to choose a number. A is a number, and I have to tell you what number are you supposed to use for this equation to hold, that the probability of all of them annihilating is the Kaufman invariant of the knot. And it depends on the particular type of particle that you've created, and they come in different classes. For those of you who are experts, these are the Chern-Simons field, Chern-Simons theory, SU2 level K, but I'll just call them class 1. You choose A equals e to the I pi over 3, complex phase. And in this class are what substances did we start with here that fit in this class? Well, there's substances that if you're a physicist, you may have heard of, but most things, I'll explain what this is at the end of the talk if we have time. So most fractional quantum Hall effect, quantum Hall, fits in this class. Fractional quantum Hall is two-dimensional electron systems in magnetic field, mag field. Class 2, you use a different value of A, e to the 3 pi I over 4. And there's a lot of things in this class. If you're in the physics field, you may have heard the word Majorana. Anyone who's talking about Majoranas is probably talking about this class, more or less. So there's some rare fractional quantum Hall effect. Again, if you're in the field, the so-called 5/2 state is in that category. Some 2D superconductors. Conductors fit in this class. Right now, people are interested in uranium tellurium 2. Those are a bunch of, a compound made of some interesting elements. Iron, tellurium, 0.55, selenium, 0.45 is another one that people are interested in right now. Helium 3A, superfluid films, always films, because we're always talking about a two-dimensional system. So what is helium 3A? Helium, if you remember your periodic table, has atomic, well, it has 2 protons and 2 neutrons, usual helium, but there is this sort of sister of usual helium called helium-3, which is missing 1 neutron. And you can make this in nuclear reactors and so forth. And it's rather expensive to make this stuff, helium-3, but people do make it and they do experiments on it. And it's actually quite useful for some things, particularly. Well, actually, it's useful in the anti-terrorism effort, because it turns out that you make good detectors of radiation with helium-3. But anyway, if you take this helium-3 and you cool it down to less than 1 millidegree Kelvin above absolute 0, it becomes a superfluid, and that fits in this class 2. And then there's a huge effort to engineer engineered samples, engineered two-dimensional or one-dimensional systems in order to be in this class 2. This engineering effort is led by Microsoft, who has been dumping tons and tons of money into trying to construct materials that live in this class 2. Then there's class 3, where you take a different value of a equals 3 pi I over 5, and there's only one known example of this, at least that I know of. Fractional quantum Hall again, quantum Hall, which I'll explain later, and with so-called 12/5 state. Okay, so why is all of this interesting? Why is it interesting that the probability of all these things annihilating is given by the Kelvin invariant of knot squared? Well, suppose you wanted to compute the Kelvin invariant of a really complicated knot. Suppose someone gave you a really complicated knot, and you know, you didn't know what the Kelvin invariant is, but you wanted to compute it. Well, we know that computing Kelvin invariance of a knot is exponentially difficult. If you had a knot with 100 crossings, it would, you know, take the 1,000 years, the world's biggest computer, to calculate the Kelvin invariant. But suppose you had a bunch of these particles in your laboratory. You could put in energy to create lots of these matter-antimatter pairs. Then you could just drag the particles around to form whatever knot you like, form the knot, whatever knot you like, complicated as you want, and then bring the particles back together like this, bring the particles back together and measure whether they annihilate or they don't. And the probability of all of them annihilating is the square of the Kelvin invariant. So by doing this experiment many, many times, you can make a really good estimate of the Kelvin invariant of a knot. So these particles, these two-dimensional particles, 2D particles, can compute Kelvin invariant, Kelvin squared of a knot. And the world's biggest computer can't do this. So what this means is that the computational power, compute power of this quantum system is somehow greater than compute power of all of Google. Any classical computer that you can come up with. And this statement is rather interestingly was made back in 1980, probably for the first time, by a mathematician by the name of Yuri Manin. And Yuri Manin realized that quantum mechanical systems are very, very, very hard to simulate on a classical computer. If you have a big quantum mechanical system with lots of quantum mechanical particles, you could use all the computing power of Google and you'd still not be able to simulate it accurately. But somehow or other, the quantum mechanical system knows how to simulate itself. It knows how to follow its own equations of motion. So somehow or other, it has computing power, which is greater than the computing power of all of our the computers that we have on Earth. So this was about a year before Richard Feynman started getting interested in what you can do, what you can compute with quantum mechanics. And what Richard Feynman added to the story, he says, well, it's maybe not so interesting to compute your own equations of motion. Can you compute other things? Maybe you're not so interested in computing the Kelvin invariant of complicated knots. But it turns out that the ability to calculate the Kelvin invariant of complicated knots is equivalent to the ability to do lots and lots of other interesting computations known as quantum computations, including some examples that I'm interested in. Quantum computation is simulating other quantum systems. So any one. Yes.
So Steve, there's a couple questions in the question answer before you get too far ahead.
Okay.
Maybe, yeah, here I'll read them. There's a question from Mankoba Schwer, who's asking, what's the name of the particles that have this topological property?
Yeah, good question. So generally, these particles are called anyons. So anyons, and that name is actually kind of a joke due to Frank Wilczek, another Nobel laureate, won his Nobel Prize for so-called asymptotic freedom, something very important in high energy physics. So anyon, this any means anything else that you don't get in regular 3 dimensions. So these anyons only exist in 2-dimensional systems. There are lots of particles that you can have in 3 dimensions, fermions, bosons, lots of examples of these, like electrons and protons and neutrons and pions and so forth. And anyons was termed that because it's anything else, the things that don't exist in 3 dimensions. The other question?
Yeah, there was another question from Nabin Gurjal, who asks, you assign this D for all loops independent of its properties, such as shape and size. Is there any analogous physical system where you can do that? I guess you want some intuition for why it doesn't depend on shape and size and how that works.
Yeah, no, that's the big surprise, actually, that most physical systems do not have this property. It's a really unusual property that you can have quantum mechanical systems that do not depend only. I mean, not only did I assign D to depend only on not on the shape and size. For example, in this picture, the Kaufman invariant of this knot doesn't depend on the shape or size either. It only cares that the 2 are linked, like that. But I can stretch them and pull them and deform them any way I like, and it's still going to give me the same Kaufman invariant. This is a very special property of these particular types of particles that live in 2 dimensions plus time. So there aren't very good classical analogs of this. Other questions?
Those are it.
Okay, so quantum computations, simulating other quantum systems, which is systems is one thing that that I'm particularly interested in because I study lots of quantum systems. But the rest of the world is interested in is factoring large numbers, So we know about that if you have a number like 15, its factors are 3 and 5. We know that. But if you have a very large number, like a number with 1,000 digits or something like that, it sometimes can be extremely hard to find all the factors of that large number. It's obvious if it's divisible by 2, it's obvious it's divisible by 5, but it's really hard to tell if it's divisible by some 500 long digit long large prime number or something like that. And factoring large numbers, it's something that very large computers can't do, and quantum computers, it turns out, are very good at doing this. That was a big surprise due to a very smart mathematician by the name of Peter Shor. The algorithm for factoring large numbers is known as Shor's algorithm. And this algorithm made the world interested in quantum computing. And the reason why is because most encryption, most codes, most passwords that you plug in are somehow relying on the fact that large numbers are hard to factor. And if you had a quantum computer, you could break into essentially any bank you want. So this means a couple things. First of all, a lot of people in the world are now very concerned that someone's going to build a large quantum computer and start breaking into banks. So they're thinking about what algorithms do we have for encrypting things which do not rely on factoring. And lots of governments are spending a lot of money to have factoring algorithms so they can break codes that they've wanted to break for a long time. So anyway, that's one of the reasons why people got really interested in this. Now, the idea of doing quantum computation by making knots is known as topological quantum computing. I'll write that down. Topological quantum computing. And it's credited to Michael Friedman, who is another Fields medalist. He won his Fields medal for work on the Poincare conjecture, and another very brilliant person, Alexei Kitaev. Okay. Now, it seems I'm very close to out of time. I was going to say a couple words about what is fractional quantum Hall effect. You know, since I listed it off several times here as being some of the physical systems that have these properties. Is there about 5 minutes remaining, or should I wrap it up?
Go ahead.
Go ahead. Okay, so let me give a really lightning introduction to what is fractional quantum Hall effect. Fractional quantum Hall effect. Quant Hall effect. I hope there are no experimentalists who study this in the audience, because they'll kill me for saying this. So basically, what you take is you take two-dimensional electrons, you add a magnetic field, and then you cool it down to low temperature in a big fridge, and out comes fractional quantum Hall effect. And it's really that simple. And now there are many different fractional quantum Hall effects. They're labeled by a number nu, which is a ratio of two small integers, p over q. And this is basically some dimensionless ratio of number of electrons divided by number of magnetic flux. And we want to keep it to be an integer ratio. Now, how is it that we know that this fractional quantum Hall effect has this interesting topological property? Well, in order to see fractional quantum Hall effect, you have to be able to cool it down to less than 1 degree Kelvin. And that's pretty hard to do. It makes doing any experiment extremely difficult. But there is one experiment that's fairly easy to do. So you take your two-dimensional sample, you can have any shape you like this, and you attach electrical contacts to it, like this, 4 electrical contacts along the edges, and you run current between 2 of them, and you measure voltage between the other 2. And if you do the experiment like this is what's called the longitudinal voltage, you get the answer 0 voltage at all. And that means what you have is basically a superconductor or a superfluid. It means that there is no resistance, no voltage drop, no resistance at all to the current flowing. So this is like a superfluid. Now, that's a fairly easy experiment to do. There's one other experiment that's even more interesting, and that is to topologically cross the current and voltage leads. So let me topologically cross the current and voltage leads like this, like that, like this. And this is known as the Hall voltage when you have crossed leads. And what you get is h over e squared times the current times this ratio q over p. These are the small integers that we have up here. Now, this precision with which this voltage is measured is correct to one part in 10 to the 10th. That's like measuring the distance from Oxford to Michigan to about a centimeter. It's an astronomically precise measurement, which is done on a sample with arbitrary shape, arbitrary size. It doesn't matter how you attached the electrical leads, you always get exactly the same result, correct to one part in 10 to the 10th. And that's telling you that something topological is happening, because you can make this have any shape you want, you get the same answer. It's very unlike measuring voltage in, say, a bar of copper, where if you move the contact just a little bit, you'll get a different voltage. So it's an extremely interesting quantum mechanical effect. Now, the one last thing that I want to say is what are these particles that that you want to drag around each other? Well, from this experiment, we discovered that we have a dissipationless superfluid. Dissipationless superfluid means that vortices in the superfluid are persistent. They last forever. Nothing makes them decay. So these vortices in the superfluid will last forever. And these are the particles that we want to drag around each other to form knots. So this is actually very, very much like what Kelvin was thinking about 150 years ago. It's vortices in a superfluid that we drag around each other, which we form knots with. The only difference in what he was thinking is he was thinking about knots in a 3-dimensional superfluid. And here we have a 2-dimensional superfluid, but time is our 3rd dimension, and we're forming knots in our two-dimensional plus time as the third dimension superfluid. But other than that, he's actually got things pretty close to right for what it is we've been trying to do. And I think I will leave things there and take any further questions that people might have. Thank you for your attention.
Thank you so much, Stephen. That was a wonderful talk, very
You're welcome.
entertaining and very enlightening. So are there further questions for Stephen? Go ahead, type it into the chat or put in the question and answers.
Oh, thank you. Someone says it was amazing. Thank you. Thank you very much. Don't be afraid to ask questions.
Well, we're waiting for questions. Perhaps I can ask a question. So 2D systems have all these incredible topological properties, as you've shown. Is there anything interesting in the 3D bulk system that remains?
Yeah. So, well, okay. So is there anything interesting in 3 dimensions? So in 3 dimensions, you can have physics like this as well, but you can't form knots in one-dimensional world lines in 3+1 dimensions. That's a statement, that's a topological statement, which is completely obvious to some people and completely impenetrable to other people. I can explain it if you want me to. But for those people who think it's completely obvious, what it means is that you can, in 3 dimensions, if I have a 3-dimensional system, so here's my 3-dimensional system, like this, if my particles are not point particles, but the particles themselves are loops, then I can take another loop and pass it through this loop. So I take another loop and move it through this loop or something like that, and do something non-trivial, or take a particle, which is actually a point, and move it through this loop and do some non-trivial braiding that way. But you can't non-trivially braid a point with a point in 3+1 dimensions. And I'm happy to explain that comment if no one has other questions.
There is actually a question from Jacob Watkins. The question is, can topologically distinct knots have the same Kaufman invariant?
What was the question? Sorry, it didn't come out on the chat. The question, I think, was, do distinct knots, can distinct knots have the same Kaufman invariant, or do they always have to have different Kaufman invariants? So it is not true that that if 2 knots are different, 2 knots that are different could have the same Kaufman invariant, but it is always true that if 2 knots are the same, they do have the same Kaufman invariant. So it's the converse of my statement that it is not true that 2 knots are the same if they have are necessarily the same if they have the same Kaufman invariant. That's the way to put it. There are examples of 2 knots which are different, which do have the same Kaufman invariant. I think the simplest example are 2 knots with 18 crossings or something like that, which can be shown to have the same Kaufman invariant. And it is unknown if there are any knots which have the same Kaufman invariant as a simple circle. That that you can find anything whose Kaufman invariant is just D if it isn't a circle. This is an unknown open question, I believe. So I can read off some of the other questions in the talk, unless you have a different supply, because I didn't see the question about.
No. So now I'm going to the chat. So there's a question by Daniel Bazan, who asked, does the knot theory somehow relate to the path integral approach of quantum mechanics?
So there are nice ways to describe this braiding physics in the path integral formulation of quantum mechanics. It's not directly related in the sense that you can't, there's lots of there's lots of physics which can be described in the path integral approach of quantum mechanics, which doesn't have anything to do with knotting. But it's a very beautiful way to understand a lot of this knotting physics by using path integrals, and why it is that certain physical systems have this this behavior, or to some extent.
Okay, we'll take one last question from Sam Austin. What is the status of experiments aimed at factoring?
Right. So believe, I'm not sure what the largest number that's been factored is. I believe people have done 15. But even, I mean, so Google had let me put it this way. So the most spectacular, Google is leading the world right now in quantum computing. They have a really great quantum computing lab. And lots, they have a literal army of people working on this in this lab. And last year they have had a paper demonstrating what's known as quantum supremacy. So quantum supremacy is that they demonstrated that their computer could do a computation that no classical computer on Earth could do. And then after they did this demonstration, someone showed that actually, Los Alamos supercomputer working for, a year, running every single one of their, 500,000 cores or something, could actually just barely make it. And so it wasn't completely true that they've been able to do a calculation that no classical computer on Earth can do. But it's interesting because they managed to do the computation in a matter of a few minutes. So maybe it was even only a few seconds. So they're much ahead, and I think now they've improved their system now, and they may be able to do beyond what if they add just a little bit more to their experiment, they can go beyond what anyone else can do. But I don't think people have tested factoring on much larger systems, because the quantum supremacy experiment was cooked up in a clever way to be immune to lots of the errors that they get in their quantum computer. And I think to do factoring, they may be quite more restricted, and I'm not sure how large a number they could factor. It's probably not a whole lot bigger than 15. They might be able, maybe they'll be able to do, like, I don't know, 36 soon or something, but they're not factoring 1,000-bit long numbers yet. They're not breaking into any banks, and that's going to be a long time before they get that. Their quantum computer has 50 or 60 or 70 bits in it, and you need a computer with thousands of bits to do that kind of factoring, probably tens of thousands, even hundreds of thousands, depending on how good the bits are.
Okay, well, thank you so much, Stephen, for a really wonderful talk and discussion.
My pleasure.
I think everybody agrees with me that was really, really fun. So thank you so much.
Okay.
And thank you to everybody who came. If you want to stick around, just chat with Steve, go ahead. Otherwise, I'm going to stop the recording now.